In this section, we will discuss about colligative properties. These are the properties that depend only on the number of solute particles and doesn't depend upon identity of the solute particles. In other words, if I have one sodium chloride which breaks down into sodium plus and Cl minus, would have same effect as one potassium chloride which would break down into potassium plus and Cl minus. Now what are the colligative properties? Vapor pressure lowering, boiling point elevation, melting point depression, osmotic pressure. Now all these depend upon number of particles. Now vapor pressure. Because of solute-solvent interaction, higher concentrations of non-volatile solutes make it harder for solvent to escape to the vapor phase. You can see on the right hand side, for pure solvent, you can see there are quite a few gas molecules above the liquid. On the other hand, when a solute is added, in the second case, underneath the first one, fewer solvent molecules are in the gas phase. Now why it is that way? Because there is a solute-solvent interaction. That solute is going to hold on to some of the solvent molecules, and those solvent molecules cannot freely move on to gas phase. In this slide, this big gentleman represents non-volatile solute, and these small men, they represent solvent molecules. When there was no such big gentleman present near the door, these small molecules could readily go through the door to the vapor phase, because outside of the door is like a new phase, and in this particular case we'd call it vapor phase. When this non-volatile solute is present, like in this case this big guy, he can tackle a number of those small guys quite effectively, so that those small guys cannot pass through the door. Now if there are quite a few of these non-volatile solutes, the effect would be even bigger. So the question is, if solvents cannot go to vapor phase freely, do you expect the same vapor pressure as pure solvent? Obviously the answer would be no. Since some of these molecules cannot freely go to the vapor phase, you would expect vapor pressure would be lower in a solution. In this case, we are showing you an increased number of non-volatile solute. And keep in mind, each of these solute would act as a tackler. So each of them can tackle a number of solvent molecules in their efforts to go to vapor phase. So more of these non-volatile solutes are present, the vapor pressure due to the solvent molecule is going to get smaller and smaller. Now this expression, Raoult's law, that shows you the relationship between the solute concentration and change in vapor pressure. So XB is the mole fraction of solute. Here B is the solute and A is the solvent. So as I increase the number of solute particles, this is mole fraction, number of moles of say solute divided by the total number of moles of solute plus solvent. That makes mole fraction. So as mole fraction of solute is increased, as you can see, that decrease in pressure is also going to be quite substantial. In this slide, before I talk about boiling point elevation and freezing point depression, I would like to give you an idea about what boiling point means. Say I have a container here, and I have liquid here, and these are liquid molecules in here. and there's nothing on the top. It's an enclosed container. At any particular temperature, say this liquid is water, at any particular temperature, water molecule would gradually go to the vapor phase. After some time, the number of water molecules going to the vapor phase would be equal to the number that is coming back to the liquid phase. And that's equilibrium. When equilibrium is reached, there'll be no more changes in the number of molecules in the vapor phase, and the pressure at that point would be called vapor pressure of the liquid. At the increased temperature, by heating the liquid, our common sense would say liquid molecules would be moving faster, so there's a greater likelihood that these molecules would go to vapor phase. In other words, vapor pressure is going to increase as you increase temperature. As you keep on heating, at some point vapor pressure would be equal to that of outside pressure. So vapor pressure equals to external pressure. If the external pressure is 1 atmosphere, the temperature at which vapor pressure gets equal to 1 atmospheric pressure would be called normal boiling temperature. In this graph, you can see that this is the point which represents, let me show in the red ink, this is the point on the pure solvent graph that represents the boiling temperature, because at this temperature the vapor pressure would be equal to 1 atmosphere, and you can see that on the left hand side you have pure liquid, on the right hand side you have gas. So this represents liquid vapor equilibrium, and that's boiling. If you look at the left hand side, again I'm drawing another red dot. On the left hand side of the dot you have solid, pure solid. On the right side you have liquid. So this represents solid liquid equilibrium, and that's melting. So this represents melting point under 1 atmospheric pressure, and this big circle represents boiling under 1 atmospheric pressure, and that's called normal boiling temperature. Now if you have a solute, let's draw those big solid molecule with a different color of the ink. So these are solutes, so they're big. Because of their presence, they're preventing some of these small solvent molecules to go to the vapor phase. In other words, there'll be depression of vapor pressure. Remember, in order to boil it, you have to heat it so that vapor pressure becomes equal to the 1 atmospheric pressure. Now, in case of pure solvent, whatever temperature you need to heat to, this time you need to heat even to a higher temperature, because vapor pressure will be lower because of the presence of non-volatile solutes in the solution. By looking at the graph, you can also understand it. You see that solution graph lies underneath the pure solvent graph, and that's why this bottom curve is the solution curve. And if you look at under 1 atmospheric pressure, you can see that for the solution the boiling temperature is here, shown with blue circle, and this represents an increased boiling temperature. So we can now explain that boiling temperature elevation happens when non-volatile solute is added to the solution. Now in case of a freezing point gets depressed. Again, you can understand it by looking at the graph. As I discussed before, boiling point elevation depends only on the number. In this case, that number is expressed by molality. So in case you forgot the definition, molality stands for moles of solute divided by kilogram of solvent. So it's represented by small m. So moles of solute per kilogram of solvent is molality. So basically, it also deals with moles or number. As number is increased, boiling point elevation is also going to be greater. Kb is called molar boiling point elevation constant, and that would be given to you in order to solve a problem. Freezing point depression, that expression is also very similar to boiling point elevation expression. The only thing is here, freezing point goes down, the temperature goes down. In case of boiling temperature, that goes up. Again, this is molality. M stands for molality, moles of solute per kilogram of solvent, and Kf is a constant, which is the molar freezing point depression constant. Remember, in case of boiling point elevation, we had Kb. That was the boiling point elevation constant. And these values are all known, and that will be given to you in order to solve a problem. The point that is important here is the delta TB or delta Kf. They depend only on the number of particles, not on the nature of solute that you are adding. Right below this, there is one question given here. I think I have assigned similar problems from the book. Arrange the aqueous solutions in order of increasing boiling points. Obviously, you'd be looking at how many particles you are getting, basically how many particle concentrations you're getting out of these compounds. Since we don't have much space left here, so I'm going to show you just one of them, then maybe I can do the one homework problem in more details in the next section. But let me show you how we can find out number of particles out of this. Ferrous sulfate, that would break down into this is ferric sulfate, I'm sorry, this is not ferrous because of this 3. So that 3 came from iron plus 3. So 2 Fe3 plus and 3 SO4 2 minus. So altogether there are 5 particles. So even though we had 0.1 molar of ferric sulfate, but that 0.1 is now multiplied by 5 because it's no longer 1 unit in solution. So it acts like 0.5 molar solution. In case of barium chloride, there are 3 particles coming out of it. Barium 2 plus and 2Cl minus. So let me show you that. Ba 2 plus and 2Cl minus. So altogether you're getting 3 particles. So the original concentration was 0.2 molar before that ions came out of it. But then each molecule will give rise to 3 ions. So 0.2 molar becomes now 0.6 molar in concentration. So this is how you find out the particle concentration. And as I said, these properties all depend upon this particle concentration. So the higher the concentration or number of particles, the greater will be the effect. In case of boiling point, it would be boiling point elevation. In case of melting point or freezing point, it would be depression. In case of a vapor pressure, it would be depression of vapor pressure. In last slide, we discussed a similar thing for other ionic substances. In this case, we are discussing about 1 molar solution of sodium chloride that produces 2 molar solute ions, because sodium chloride breaks down into sodium plus and Cl minus. So from each unit of NaCl, you're going to get 2 particles, 2 ionic particles, Na plus and Cl minus. So boiling point elevation or melting point depression will be twice as large as 1 molar non-electrolyte like sugar. Sugar doesn't break down into any other ions. Now osmosis. Some substances form semi-permeable membranes which allows smaller particles to pass through but block larger particles. In biological system, most semi-permeable membranes allow water to pass through, but solutes are not free to pass through these kind of membranes. In this slide, we're going to explain to you if you have a semi-permeable membrane, which is this, and solute molecule on the left hand side, I'm showing you this big guy is a solute molecule, and these tiny ones are the solvent molecules which can readily pass through the semi-permeable membrane. Now the question is, if we have more concentrated solution on one side, why we are calling it more concentrated on the left side? Because of this presence of this solute. So this is solute, and there is no solute on the right hand side. So left hand side represents more concentrated solution than the right hand side. Now I can increase the number of solute on the left hand side to see a bigger effect. Now just remember this experiment that gives you an idea about the flow of liquid from what direction to what direction. So imagine each of these solute is like a big guy, and they're pushing this membrane along this direction. Now as this membrane pushes along this direction, the little water molecules along the way would pass through it. So in other words, from these simple hypothetical experiments, we can tell that solvent molecules, in case water molecules, would pass from less concentrated. So this is less concentrated, and left hand side is more concentrated. Now why right hand side is less concentrated? Because there is no solute, and on the left hand side, to make it simpler, we have one solute molecule, that's the big guy. So always is the solvent particles from less concentrated side goes towards more concentrated side. So keep this in mind. Now in this slide, we are seeing that this big guy has already pushed that permeable membrane, semi-permeable membrane to the right, and that pushed some solvent molecules from right hand side to the left hand side. So here we establish the direction of solvent movement from less concentrated to more concentrated solution. In osmosis, there is a net movement of solvent from the area of lower solute concentration to the area of higher solute concentration that we already have established in last two slides. So this is the same thing that you're looking at now. Basically, to stop the flow of liquid, you have to exert pressure that they're showing on the third figure. So applied pressure stops the net movement of the solvent. So if you know which direction solvent is coming from, then you can put pressure on the opposite side to stop it. And that's how you can find out what is the osmotic pressure. Osmotic pressure is represented by pi, and that's given by mRT. M stands for molarity of the solution, and R is the gas constant, and T is temperature in Kelvin. If the osmotic pressure is the same on both sides of a membrane, then solutions are called isotonic. Now this is a practical example, osmosis in blood cells. Now we already know now the theory and can predict what may be happening. If the solute concentration outside the cell is greater than the inside the cell, the solution is hypertonic. Water will flow out of the cell and crenation is going to result, and that's what you're going to see on the right hand side. In this slide, we are considering that solute concentration outside the cell is less than the solute concentration inside of the cell. And this kind of solution is called hypotonic. And as you know, that solvent would flow from low concentrated side of the solution to high concentrated side of the solution. What that means is solvent molecule would now enter into the cell and causing hemolysis.